There is a whole new world, from the confinement of laptop to infinite computes of cloud platforms. Hello. For decades, the standard hardware configuration for a data scientist or machine learning practitioner was a high-performance local laptop or a heavy desktop workstation. Traditionally, manipulating, cleaning, and analyzing data required writing scripts in programming languages like SQL, Python, or R, executed entirely on local processing units. When data fit comfortably within a machine's RAM and CPU limits, local execution offers a highly tactile and immediate feedback loop. However, as datasets have expanded into massive, near population-level big data, the limitations of physical hardware have become glaring bottlenecks. Relying purely on local resources forces practitioners to constantly wrestle with storage thresholds and processing capacity. Anyone who has lived this knows the ritual. You submit a job in the morning, head off to do other things, and finally get your result around dinner time. Assuming the machine doesn't hang halfway through, in which case a reboot wipes the slate clean and the whole day is gone with it. Next, you have to spend the evening drafting an apology to your boss for a deadline that the hardware, not you, messed up. To rectify the situation, data science is rapidly moving away from laptop computing to cloud computing, establishing an environment where scalability and real-time collaboration are standard prerequisites rather than luxury upgrades. The drivers of cloud migration. The pivot toward the cloud is fundamentally driven by the sheer volume and diversity of modern datasets, alongside the heavy computational demands of generative AI and deep learning. Cloud computing offers a virtually limitless storage capacity and processing power compared to traditional local machines. This vast infrastructure allows data analysts to easily ingest, store, and process big data, performing complex, distributed computations that would simply freeze or crash a standard laptop. Beyond raw computational strength, cloud ecosystems transform how engineering teams operate. Instead of working in isolated local silos, where sharing code, data snapshots, and environments introduces frequent version conflicts, cloud platforms provide centralized data access and real-time collaboration. This collaborative fluidity is critical for distributed or remote data science teams who must jointly manage pipelines, track data provenance, and deploy models into production continuously without relying on local machine configurations. The global cloud infrastructure market is characterized by a fascinating geographical duality or bifurcation, dominated by distinct American hyperscalers and rapidly expanding Chinese providers. The Western hyperscalers. Hyperscalers are massive cloud service providers that operate thousands of servers and millions of virtual machines globally to offer highly scalable, on-demand infrastructure. Globally, the market is historically anchored by the big three Western providers. Amazon Web Services, AWS, is the pioneer of infrastructure as a service. IaaS, highly favored for its mature, extensive ecosystem of developer tools and robust enterprise data pipelines. Microsoft Azure is a dominant player heavily integrated into enterprise IT environments, which leverages deep corporate relationships to deliver seamless hybrid cloud deployments. Google Cloud Platform, GCP, is renowned for its cutting-edge data analytics, native Kubernetes integration, and powerful managed machine learning frameworks. To maximize their reach and deliver specialized capabilities, these hyperscalers maintain vital strategic partnerships with industry-leading software vendors. A prime example of this ecosystem integration is found in data analytics, where SAS Institute, a long-standing leader in advanced analytics, has deeply integrated its modern, cloud-native platform, SAS VIA, with Microsoft Azure to give organizations scalable, high-performance computing directly within their cloud environment. Similarly, Salesforce, the developer behind the renowned data visualization application Tableau, has re-architected its deployment strategy through Hyperforce. Hyperforce is Salesforce's next-generation infrastructure architecture built natively on hyperscaler public clouds, with AWS as a primary substrate. This allows enterprise users to run Tableau and other Salesforce applications with the elastic scale, rigorous compliance, and localized data storage of the global OS footprint. These deep integrations demonstrate that modern cloud platforms are no longer just raw infrastructure, but collaborative environments hosting specialized enterprise ecosystems. This trend toward deep ecosystem integration has culminated in an era of radical, multi-cloud interoperability, championed aggressively by Oracle Cloud Infrastructure, OCI. Long regarded as an enterprise database giant, Oracle has rapidly expanded its cloud footprint by optimizing its infrastructure for high-performance bare metal AI training and signing massive infrastructure deals with leading AI labs. Rather than forcing organizations to choose between walled gardens, Oracle has shattered traditional competitive boundaries by launching direct, native partnerships with the Big Three. This allows enterprises to run Oracle's dedicated database hardware directly inside rival data centers, allowing users to feed corporate data straight into AWS or Azure machine learning models. As a result, the modern data professional is no longer tethered to a single provider, but instead operates across a fluid, highly interconnected web of cross-cloud alliances. The Eastern powerhouses. Concurrently, Eastern tech giants have built massive cloud ecosystems tailored to massive consumer markets, local regulations, and independent AI infrastructures. Alibaba Cloud is the largest cloud provider in mainland China and across the broader Asia-Pacific region, commanding a dominant local market share fueled by high-velocity e-commerce and retail analytics infrastructure. Tencent Cloud is a massive digital competitor that excels in building specialized infrastructure for high-concurrency gaming, social media data, and advanced, multi-agent orchestration development platforms. Huawei Cloud is a fast-growing infrastructure powerhouse that has established a major footprint in both public and private sectors, heavily focusing on native NPU clustering and enterprise AI deployments. This global multi-cloud landscape ensures that whether an organization is operating under Western data frameworks or navigating regional Asian data localization mandates, there is a hyper-scalable platform equipped to handle intensive machine learning workflows. The decentralized counter-trend. While the general trend points toward aggregating resources into centralized data centers, the industry is simultaneously observing an important counter-trend, or a return to the source. Sending massive streams of raw information from localized sensors to a distant cloud introduces noticeable network latency and steep data egress costs. Consequently, specific tasks are moving back to local hardware through architectural frameworks like TinyML, which runs machine learning models on low-power microcontrollers inside wearables and IoT sensors rather than sending all data to a centralized server. Similarly, localized inference uses optimized small language models, SLMs, directly on consumer devices like smartphones and laptops. This hybrid orchestration creates a highly efficient division of labor. Massive, resource-heavy training runs are offloaded to massive cloud GPU clusters, while instant, privacy-critical, and latency-sensitive deployments run locally on edge hardware. Questions for you. There is no silver bullet. While cloud computing makes high-performance computing and big data analytics available to more people, some issues demand our attention. As cloud infrastructure becomes the default for enterprise data workflows, are we risking a severe skills gap where future data scientists lack the fundamental knowledge to optimize, compile, and run code efficiently on resource-constrained local hardware? How will the deepening architectural split between Western hyperscalers and Chinese cloud ecosystems impact global open-source collaborations and the cross-border deployment of multimodal AI systems? Given the rising energy demands and complex financial structures of modern data centers, at what point does the cost of constant cloud data egress and variable compute subscriptions outweigh the long-term capital investment of building specialized local hardware? What do you think? I'd love to hear your perspective. Please drop your comments here. Thank you for watching. Goodbye.